start all my timers to try and keep me on track. Hello, I'm Simon. I'm in the core dev team here at Redgate, looking after our internal systems, and I'm going to spend half an hour talking you through a couple of aspects of our internal systems. So this is a talk in two big halves, which are microservices and how we use them in core dev, and then a separate kind of related piece of technology, what event-driven means to us and how we use it. I've split the talk down into four major parts. So I'm going to talk in kind of high level about services, and I'm going to talk in some kind of detail and specifics. There will be a few screenshots of little bits of code. Then I'm going to talk in kind of high level about the events, and then delve down into the detail of that. So I sent this slide deck out for review to a couple of members of core dev, and about a minute later, Matt Burton wheels over to me. He says, I'm really sad about the start of the talk. I'm really sad about the name. And I was like, oh, have you got to slide 5 yet? He said, no, I haven't got to slide 5. So we've got a bait and switch here, I'm afraid. You're all in the room. It's too late. You can't leave now. Microservices is this brilliant, very common terminology that gets used, gets spread around. But it's not a term that we tend to use. It's very buzzwordy. And I can see the utility of it. I know that the guys who created it had a specific vision in mind. They had a piece of information they wanted to get across with the term microservices. But it's not something that we care about. The micro part in particular tends to be thought of as meaning the size of the code base. Like it's very small. That's fine. We like small code bases, but it's not an important, critical piece of thinking. So I tried to kind of construct a little mini taxonomy of the stuff we do have. This is a bit artificial for the purposes of this talk, but it's to try and give you a flavor of the stuff that we actually have. So we have HTTP APIs, and this is the thing that we would probably call a service most of the time, in that it has a job of owning a piece of data, a piece of state within the overall system. So it might own invoices, or it might own kind of some monitoring data or something like that, but it is responsible for having a database underneath it, and when you query it, it will tell you the state of that, allow you to make changes to it, and so forth. We have a set of interconnections. So we have a similar requirements for third-party systems. So maybe they're holding data, they're holding state. Again, we want a system that wraps those and allows us to make mutations to them or receive data back from them. We have a kind of meta monitoring need. We have to watch the systems as they interoperate. We have to watch third parties to check they're operating correctly. We want to know when things go wrong. We want to be able to record it. We want to be able to dashboard it. We want to get information back. So we have monitoring systems. We'd like to be able to perform actions on some kind of schedule or delay. So once a month, we run a piece of renewals generation. So all the renewals that are coming up in about 4 months' time get generated on the first of the month. We have similar kind of other processes where just on a regular cadence, you want to do something within the system. Thinking kind of ahead to the second half of the talk, we just have events. I'm not going to detail what those are at the moment, but we generate stuff happens, and we want to respond to it. An invoice is created, we want to provision some licenses, that kind of stuff. And kind of lastly, but perhaps most importantly, like there are actual people who want to see actual results and make actual changes. So we need to put some web UIs in place around these things. So that's kind of the last big component. Again, these are sort of artificial bags that I've created here, but roughly speaking, that's the kind of numbers of things we've got. This came as a surprise to the number of people in core dev that I put it in front of. They're like, we don't have like 25 web apps, do we? And I was like, well, hang on, this is the list that I've got. And they're like, oh, wow, yeah, we really do have 25, So that's just over 100 different bits of technology that are somehow their own little unit, which is quite a lot for 12 people to look after, really. So here's a high-level example. We have a piece of UI, which you're not supposed to be able to read, but that's the account admin portal. It lets you view a customer's licenses. When the web browser hits the web portal, some things happen in the back end. So the first thing is that website has been spun up with a connection to our internal config server. So that internal config is a separate service in its own right, and it tells the account admin website where it should get its connections, what its settings are, what its config is. So that internal config will say, you need to talk to the products API, which is here. You need to talk to the licenses API, which is over here. You need to talk to the commercial data API. You probably need to talk to authentication to find out who this person is and whether they're entitled to actually see the things that they're requesting. You need to talk to the contacts API, which is one of our interconnects. So that talks out to Salesforce, where our contacts data is stored. So all of that kind of stuff comes together to generate the response, which is the website that the customer sees. Why would we do this? Why would we break it into 100 little bits? So firstly, we get to surface complexity, which is very useful. It doesn't necessarily make things less complex, but we get to see where the complexity is. We get to deal with third parties pretty much the same as we deal with internal systems. They're just an API. They look like anything else. It happens that they're backed onto the cloud or some other third-party storage. It's very easy to work with. We have a small code base. We can add and delete, remove things very quickly. Infrastructure typically doesn't pollute the system services. So when you crack a piece of code open, you're not seeing logging, you're not seeing error handling, you're not seeing authentication. Those things have all been dealt with elsewhere. You just see purely a piece of code that deals with the business logic that you're interested in. Very quickly go through kind of what our process is like at a super high level. We dev locally, and we can spin up a local environment that sort of mimics live fairly closely. It's okay for testing purposes. We do have kind of PowerShell support to spin those up. We also have Vagrant support if you want to spin up a VM with everything on. Obviously, everything gets piped through TeamCity, just like every other build in the business. And then we use Octopus. We will deploy branches onto UAT for testing occasionally. Anything that goes to master, our rule of thumb is it can be pushed live, and it should be pushed live. So when a PR goes through, you can expect to see your PR go live, even if you're not personally the one that pushes it, because somebody else might. Because these are very small blocks of code, we can get very close to having 100% unit test coverage, because the business logic is very well contained, and there's typically only small pieces of spinning up the service and actually connecting to config that remain untested. We often break changes down into little parts, again, because of the way the system is broken up into chunks. So we can change, say, create a new API that just sits there unused, then we can do some data migration to support that. Then we can upgrade all the consumers to the new API, and then we can clean up, tear down old APIs. So we'll do a kind of componentized kind of split of the work. So move on to the structure of an API. These things are really simple. Like, that block diagram is probably overcomplicating the whole thing, to be honest. So the exceptions, repositories, services are mirrored between a client layer. So we'll take that client assembly and we'll go and build it into any consumer that needs to use the API. Technically speaking, we wouldn't have to, because if we wanted to write, say, a web app against this, it's just a sort of pseudo-RESTful API, so you can just go and make HTTP calls against it, that's fine. But if we were writing some C#, why wouldn't we just use a client library? So that's how we tend to wire the services together. Each one will have a set of bindings that take some incoming JSON, typically, and turn it into a local object at a kind of API layer. And then you'll have business logic down in the core. So everything kind of in the yellow boxes at the bottom will be unit tested. That's the thing that you'll crack open and look at it and just go, what does this service actually do? That's what you mean. You mean that core logic. You don't care about controllers, bindings, things like that. They're just wiring. So a little bit of code. Not sure you're going to be able to see this, but the point of these three really is that this is the licenses API. It's a fairly sort of reasonably significant piece of the, the overall system. It's really not a lot of code. There are really not very many folders and CS files actually in here, particularly if you look at the licenses core over there on the left. It's got factories, identifiers, records, repositories, services, and that's it. You could open that up and you could quite easily understand what was happening from a kind of a service point of view. We have a set of utilities that let us build these things quite quickly. So you can see that there's a big list of dependencies over there on the left. They're all shared stuff that just makes writing services easy. So again, the actual API assembly over here on the right is very small, and the reason it's very small is that the majority of its common functions as a service are just held over there on the left-hand side in a set of logging, queuing, configuration, client libraries for other services, and so on. Sorry, I realise I'm talking really fast, but it's because I'm aware of how many slides I've got and how much time I've got. So the internal structure of a service is even more trivial than of an API. It has to do even less actual stuff. Basically, we have a little program. It just starts a service. It's a handful of lines of code. Message handlers literally just take bindings and call a function, and that's it. And a service would probably have, I think the one that has the most has about 6 message handlers in it. So these are tiny little bits of code. And then you have a core at the bottom, a set of repositories, logic, connectors. But again, very small amounts of code, very easy to open and reason about. We have, again, just standard wrappings for utilities. This is what makes the kind of core logic easy to reason about. So again, we have a connection to the internal config. We have standard assemblies for things like logging, for things like queuing, for things like just being a service and spinning up on a Windows host. We have a set of client libraries, so you probably can't read it, but it doesn't matter, but there's a Salesforce client library there at the bottom. This view, I hope it kind of illustrates that the third-party libraries and the other API libraries just kind of look the same from the perspective of this service. It doesn't care that it's talking to Salesforce versus talking to the licenses client. Those two things, one of them happens to be a third party, one of them happens to be internal. This service just does not care. So we wire them together. Again, very small bits of code. It's one of the main messages of this talk is there's very little code in this stuff. So we use a machine name typically as the environment, but there are a few machines that have kind of a special environment variable to say this is live or this is UAT or something like that. But mostly, so I have dev Simon H3 is my machine name. There's a set of config in the shared repository that is keyed against my machine name. So whenever I spin services up, they just get all that appropriate config for their location. And again, there's no code for me to write. When I create a new service, this just happens for free. So any connection string to any other service that I might want or any database that I might want, the service just gets it for free. And then this is an example of getting a connection. So we want to talk to the REST client for Salesforce here. We just grab the settings, and that's it. We've got a connection to the REST client. and that works on every environment and every machine, every developer's machine. Nobody has to tinker with kind of app.config or anything like that to get it working on them, on their local environment or their Vagrant box or UAT or live or anything else. So things do occasionally go wrong. Things go bang. When things go bang, we stick a message on the bus. So either services, web APIs, whatever, throw exceptions. Those exceptions are caught and just get dumped onto the bus. Monitoring does the same thing. It sits and watches third-party systems. If it sees something that goes wrong, dumps a message onto the bus. We can then do whatever we like with those. So they will get pumped to Slack appropriately. They will end up in Elmer, where we can go and visit a website and go and see what the contents are. We can populate a dashboard, stick them in Librato or something like that and see how often these happen. Everything from an error perspective is routed the same way and is routed to whichever kind of is most convenient output for us. Sorry, that's really quick, I appreciate, but we're now moving on to part 2, which is events. So back in 2013, we wanted to do some metricization of all the systems we had, and event buses looked useful for that, so we generated some metrics and stuck them on a bus. And we're like, oh, that's interesting. And Matt Burton was very sad about this because he said that's completely the wrong piece of code. He's like, that's from 2013. We don't do anything like that anymore. It's horrible. No. But I wasn't going to take it out just for him, so bad luck, Matt. But we then kind of realized that we can put system events and stuff. It doesn't have to be about metrics. We can actually start to use these as an integral part of the system processing. I'm going to loop back to what I said at the start of the talk. Not everything is events, okay? We talk about events a lot because they're really useful and really interesting, but the Redgate internal systems as a whole is not all about events. There's all the other stuff. There's the HTML, JavaScript, HTTP APIs, webhooks for incoming things. We store data. There's lots of other concerns we have, but events are this part of the talk and what you'll hear us talk a lot about, but please bear in mind there's a lot of other stuff going on as well. Whenever I end up talking about events and about kind of RabbitMQ and stuff like this, and you'll have heard ThoughtWorks talk about this when they were in the other week, there's a load of problems that we do not have to solve. Everybody comes along, oh, but how do you get end-to-end consistency across the whole system? How do you get transactions working? We don't care. It just does not a problem. Okay, if there was any point where it was a problem, we would go and solve that particular problem. But we don't have to have complete consistency across the system. We don't have to have 100% availability. The whole Lamport vector clocks got mentioned the other day. They're brilliant. Go and read the paper. It's really interesting. We don't care. They don't solve a problem we have at the moment. Okay, so just having little systems that react to the environment around them and putting those little services together is good enough for what we need. It also means that if you think about building a system that incorporates third parties, you can't put transactions around your third parties anyway. Okay, they're just HTTP calls or whatever, or you're waiting for webhooks. You're not going to get transactional consistency in your system if it incorporates third parties. Bad luck, live with it. Come up with another way of dealing with it. The other question is, isn't it slow? Which is an interesting one because I think it tends to be predicated on the idea that you have a user and the user clicks a button and then all of the things that have to happen and you get a response back to the user immediately. But that's sort of not really the case. So when a customer comes along and they click buy on their shopping cart, as long as we've recorded the fact that they've clicked buy on their shopping cart, we can then return to them and go, yep, you're good, you can carry on with what you're doing. And then eventually we might raise an invoice, and then eventually generate them a serial number, and then eventually email them the serial number. It doesn't all have to happen by the time they get a response to their HTTP request, okay? Which is the point. So the question about speed is kind of a bit inappropriate quite often. events versus messages. So you could put messages on the bus for a number of different ways, and particularly request for thing to happen. So please can this happen? So far we've resisted that. We don't have commands of any type at the moment. We only have events, and we only have things that respond to events. I think the most important reason personally is because it encourages the thinking about loose coupling. It encourages you to think from the recipient's kind of point of view, in that you might have many things which are interested in the state of the system just changed and then wanting to react to it. And I think that's whereas if you're putting a command on the bus, you're assuming that one and only one thing will deal with that command. It's the change in thinking which I think is most interesting there. So once we've dumped all these events onto the message bus, part of the benefit we see is that we get a number of things for free. Errors are kind of quite clearly visible because, again, they're just raised, exceptions appear, all exceptions from all services end up on the bus, and we can stick them in Slack, we can stick them on pretty graphs. Those aren't actual graphs of errors, those are graphs of user interactions of some kind, I can't remember which. But we can also inject either manually or by other processes. We can jump into the middle of a piece of processing. So if something fails halfway through, we can fix the downstream system that was failing, then resend the message, and then it will just carry on, which is something that we occasionally do in order to fix things. So if we had a system which was fully wired together, you wouldn't be able to jump into the middle. You'd have to either manually fix downstream data, or you'd have to revert upstream data and then start the process again or something like that. We can just literally jump into the middle, insert the sort of middle event, and the follow-on systems, all of them will just complete. The bus technology we use kind of makes it trivial to have retries. So if your database has gone away temporarily, or there's some other transient failure with your service, you can simply reject the messages, and the bus technology will sit there and queue the messages up until you're ready to handle them. If there are permanent failures, it will drop them on the floor. It's not entirely for free. We did have to build a little service, but we can have time-delayed events. So we can simply take an event, wrap it up, and say, can you send this to me in an hour's time? Or can you send this to me in 30 days' time, please? And we'll store that in a database and then spit it back onto the bus at an appropriate time. This was really cool, and this was the kind of inspiration for part of this talk. We did a piece of work on requesting ownership, so customers coming along and wanting to request ownership of a license that they weren't currently an owner or admin of. And you don't have to read that, that's not the point of it, but we sketched out all of this stuff on the whiteboard, all of the systems. Each box there is a system of some description. And we drew that all out, and we went, what do we need to change to do this? And it was little bits of tinkering, little bits of rewiring that we had to do. And as it happens, it was Matt who's getting mentioned an awful lot in this talk. That's not deliberate. Matt stood there and he went, what's the opposite of tech debt? It's like we've basically virtually built everything we need to implement this feature. I was like, well, I guess it's technical credit then, isn't it? But that's really cool. We'd like built all the stuff. All we had to do was rewire it in a different way. So I've got only a few minutes left, but I'm going to go through some technical detail now, because most of you are technical people and you're probably interested in how RabbitMQ works and how the bus works. So that grey box in the middle is like the bus, and it has these two concepts. It has an exchange and a set of queues. So a message comes in, it will be matched against a header onto a set of queues which can accept it. So that message will get copied onto each queue, and then consumers will pull it off the queue and enact it, handle it. So messages have routing keys and queues have bindings, and those two things simply match up. So, excuse me. So if that top queue has a binding for ABC and the bottom queue has bindings for ABC and DEF, then the top message will get sent to both queues. The middle message will get sent to just the bottom queue, and the bottom message has no bindings, so it will get dropped on the floor. A single queue will give each of its messages to a single consumer. So you can attach multiple consumers to a single queue. If you wanted to do a kind of round-robin handling, if you wanted to share out the workload, you'd attach multiple consumers to a single queue, and each message would go to just one of those consumers. So interacting this slide to this slide gives you a kind of full ability to send messages to many different places, and then to send many different consumers a fair share of the messages. This is the other question I always get asked, is like, but what happens when the network goes down and they can't see the queue? So services all have a local queue that they can write to. So they don't have any problem when the network goes down. It means that they can't read incoming events, but that's fine. They just sit there and spin their wheels. They can write all the outgoing events that they need to. The only time that this fails is if that local bus fails, which happens pretty rarely, typically in kind of catastrophic situations like the entire hard disk has gone away and the queue just can't write anything. It's that kind of failure. It happens occasionally. I think I can remember it happening about twice. But basically, we then just shovel everything from the local bus into the main bus where the rest of the system can see it. Events themselves are fairly simple. They're just little blobs of JSON. They have a few little common bits. They have a timestamp. They have the message type, which is the routing key that we mentioned earlier. So this is an invoice created message. So every queue that cares about invoice created will get to see this. Have a set of headers that are mostly for monitoring purposes, and then it has a payload. Here it's the invoice ID and contact ID. Internal structure of a handler, not really very interesting. Basically, it's very simple. We have a handler method, we have a binding, and then we have a function that just kind of wires those two together. I'm very sorry about how fast I talked and how many slides there were, but there was quite a lot of stuff that I wanted to cover in a short period of time. So thank you very much.